Testing using a gas analyzer is probably one of the most efficient ways of determining if there's a fault in a system. Typically, when we have a catalytic converter code, a lot of technicians choose just to replace the catalytic converter. Unfortunately, that's maybe not always a fix for the vehicle. The catalytic converter's performance may be low and set a code due to other system problems. We have to determine what the other system problems are first. The best way to do this is with gas analysis and take an analyzer and determine what's coming out the tailpipe to figure out if the underlying problem is something from the engine control system. An imbalance in fuel mixture can make a big difference on how that catalytic converter performs. If the fuel mixture isn't correct, the catalytic converter may not even be possible to light off. And if it doesn't light off, it's incapable of oxidizing HCl and reducing NOx. That'll deem it useless on the vehicle. So we have to determine what the cause is first before we replace that catalytic converter. Replacing a catalytic converter, in a lot of cases, after a fault like that, can keep that light off for weeks, months even after that time. Unfortunately, after a period of time, the catalytic converter may be damaged from the underlying problem or the engine control problem that we have originally in the system that was misdiagnosed. So it's very important to make sure we diagnose this system properly. There are ways to do this without a lot of work on the vehicle with gas testing. The following calculations, we're going to use an Ansed lambda calculator. This lambda calculator will lead us down a path to look for the known problems that it may be when diagnosing a vehicle. We are going to be using lambda, and lambda is like a European calculation of air-fuel ratio. We haven't used it a whole lot in this country. However, it has a lot of benefits as compared to air-fuel ratio. The benefits are far more exceed air-fuel ratio than it ever has. If you're in a location where you do especially ASM testing or dynamometer testing, it's very important to use 4 or 5 gas testing and lambda calculations to repair the vehicle. Lambda is a calculation which pays particular attention to oxygen and carbon. This calculation is so much more important than what we use for air-fuel ratio in the past. Air-fuel ratio used to be a great indicator of rich or lean. It's no longer the case, and this is the reason why. Air-fuel ratios today, in some of the vehicles that we have out there, are somewhere between 9.8 to 1, as high as 25 to 1. With these calculations being so different, not within that 14.4 to 14.8 that we used to use with narrowband sensors, it's very important that we use a different calculation to identify a fault in the system. The PCM has set strategies that it uses for E85 fuels or different alcohol contents in fuel. The concern we have is if a vehicle is not made for that and able to adjust for those conditions, it's very hard to determine if that vehicle is burning properly due to the fact that it's not made to burn any more than 0% alcohol. So these calculations, even with 10% alcohol, the fuel trims can be skewed a bit, and it's very hard to determine if it has an effect on the catalytic converter. So it's very important for us to look at this in a different manner, and that is using lambda. Lambda is a measurement that determines richness or leanness without being affected by the catalytic converter. So we can actually put it in the tailpipe and get direct readings of what that engine control system is doing. Variations in the fuel, whether we're using regular, super unleaded, or E85, have a great influence on how that catalytic converter is going to perform, and engine control systems. So it's important we use a 5-gas analyzer to determine what's coming out that tailpipe of that vehicle. Lambda is presented where a number as 1.000 is the preferred stoichiometric fuel control, or 14.7 to 1 as we used to know it. A leaner mixture is going to be greater than that 1.000 lambda. So if we see anything above that, we consider that lean. Anything below that 1.000 is considered to be a rich condition, a little bit reverse to what we're used to looking at for oxygen sensor calculations. An accurate reading at the tailpipe is very important to get. Make sure it's not diluted from an exhaust leak. A diluted exhaust leak can throw our calculations off with lambda considerably and give us false indications of a problem with the system. So exhaust leaks are very, very important to catch before we start calculating lambda in the system. An incorrect diagnosis can lead us to a false repair on a vehicle in a lot of cases. So for an example, if I had an exhaust leak in a vehicle and the exhaust leak was about 10% leakage, the reading that would be taken from the gas analyzer would be plus 0.1 lambda, or approximately 10%. The effect would be an incorrect diagnosis. Imagine a correct reading of lambda of 0.9.00 with an over-rich condition. With a 10% leakage factor, this might show up as a 1.000 lambda, identifying it as no problem at all, as a good fuel mixture. This is why exhaust leaks are so important to identify. The same would hold true if lambda was 1.00 and we had a 10% leakage factor of a reading of 1.1% lambda. The calculation would be excessively lean on that system. The Ansed software that we're going to be using will identify faults in the system to lead us down a path to make a correct diagnosis on these systems. This is a screenshot of the Ansed calculator which will be used to identify faults in a system. What we do is we put in the gas readings that we have, and the lambda calculator will come up with a direct termination of what may be wrong with the car. Before identifying that a cat is faulty, we need to make sure the lambda calculations are within a certain range. A lambda calculation that it was out of its range may prevent the catalytic converter from lighting off completely. This is the reason why lambda calculations can be so useful in this field. So first verify that we have lambda, a reading between 0.995 and 1.005 lambda after a repair. This step is critical to make sure we have consistent readings outside that range. The catalytic converter may not be able to light off and be efficient. Before performing our test on the vehicle, we want to make sure our gas analyzer is calibrated. We want to make sure we have 20.7% oxygen or above. Also, the other gases should be real close to zero. Before we begin any testing, we want to verify that lambda is within fuel control in this vehicle. We want to make sure the engine operating conditions are proper before we begin any testing on a catalytic converter. In order to do that, we're going to put our gas analyzer on the vehicle, and we're going to start the vehicle up and see what our lambda calculations are. We can see this vehicle now, after running for a short period of time and it's warmed up, that lambda is within its limits. Lambda is within 0.1000 or very close to that during these conditions. This vehicle is in very good fuel control. Performing a cranking test, what we want to do is we want to prepare the car and precondition the cat. So we want to run the vehicle at a minimum of 1 minute at 2,000 to 2,500 RPMs to preheat the catalytic converter. From that point, we want to shut the vehicle down. We want to disable the ignition system as quickly as possible, keeping this to a minimum of 1 to 2 minutes. After we disable the ignition system, we want to crank the vehicle over for 10 to 15 seconds while watching the CO2 levels on our 5-gas analyzer. When the CO2 levels climb about 12.5 to 13.5%, this gives us an indication that we're able to take HC and CO and oxidize them in that converter, turning it into CO2. We can see our levels reach 12.2, 13.6, and 13.7. We're up over the 13 range with this catalytic converter. We can see this catalytic converter is capable of oxidizing HC and CO into CO2. Could do a snap throttle test. The snap throttle test is going to consist of bringing the catalytic converter up to temperature by preconditioning it. That means running the vehicle at over 2,000 RPMs for at least 1 minute. At that point, we're going to quickly snap the throttle to wide open throttle and then take your foot off the accelerator. During that time, after your foot's off the accelerator, we're going to watch CO2 emissions climb. The CO2 emissions are going to be climbed from the amount of fuel being delivered into the catalytic converter. At that point, all the oxygen is going to be used up trying to convert CO into CO2. We need to watch these levels to make sure the catalytic converter is capable of converting those CO levels into that CO2. Okay, now we can see our CO and HC are down very low. Now if we give it a snap throttle, now we can watch our CO levels climb. There is a slight delay with these gases. We'll actually see the CO levels rise like we do right now, and our oxygen levels are going to be low. Right now we're going to be looking to make sure that we have enough oxygen to convert CO into CO2. And now we can see this catalytic converter, being very efficient, is now dropping that CO level down very low at this point. One thing to keep in mind, a lot of these vehicles today are so complex with VVT tumble valves, electronic throttles. Very hard to do some of these tests like wide open throttle conditions or hold the idle at 2,000 RPMs. Do the best you can. Sometimes you may have to push the gas on and off during some of these tests to load the converter up when we're testing them, because you want to feed it as much fuel as you can in order to get the accurate test results you need out of these catalytic converters. We have a 2005 Lincoln Town Car. Possible catalytic converter failure. We're going to do an invasive test on this cat due to the fact that it's got dual exhaust with an H-pipe. We want to separate which side is which to make sure we're replacing the right catalytic converter. So what we're going to do is gain access prior to the cat in the exhaust and after the cat downstream. So what we're going to do is we're going to drill a hole inside the pipe in front of the catalytic converter to begin with. And we're going to test the gases coming out of the engine prior to the catalytic converter. Be cautious when doing this. Some systems have dual wall pipes. Drilling through that may damage a pipe permanently. And always consult with a customer before drilling into any pipe. Let's start the engine and test the gases. Okay, now we sample the gases in front of the catalytic converter. And by the way, be sure to start with a warm vehicle. We want the catalytic converters lit off before we test behind the cat. Let's test behind the catalytic converter now. Now that we have both our front and rear readings on our catalytic converter, we can compare those two, and we're looking for a 70 to 90% drop from front to rear. Comparing these readings, we can see that we have a good drop from front to rear. This catalytic converter appears to be working very well. This car, having dual exhaust, from this point, we'll have to test the other side to make sure that the other catalytic converter isn't the cause of the problem. Performing a light-off test, what we want to do is get the catalytic converter so it's cooled down. Once it's cooled down, probably approximately 30 minutes or longer, so it's not lit off, we're going to start up the vehicle. When we start up the vehicle, what we're going to look for is the highest level recordings of HC and CO during this time. When the levels are extremely high during that time, the catalytic converter is not lit off, and we're going to look at those gases flowing through the converter unchanged. Within probably 3 to 5 minutes, when that catalytic converter lights off, we'll be able to see a reduction in those HC and CO gases. We're going to make a comparison from the highest level gases we have to the lowest level gases. We should see a 70 to 90% reduction in those gases. You can do this with NOx also, however, it needs to be done under a loaded mode test. As you can see here, the levels start out high. As the converter warms up, it's going to start reducing the HC and CO gases. Typically, it starts out at 50% at 500 degrees. As the catalytic converter gets warmer, up to 1200 degrees working temperature, those gases should be at their minimal levels. We can see the levels have dropped dramatically since we first started. As we look at this, we can see the levels of CO dropping down to 11%, and we have HC down to 41% so far. The converter probably isn't totally lit off yet. However, the longer it runs, we should get it to reduce a bit more. Now we can see our levels of CO and HC are now down to a very low level. This converter is working properly and oxidizing the HC and CO. We're going to perform a light-off test. The light-off test is going to consist of letting the vehicle sit until the catalytic converter is cooled down for at least 30 minutes or longer. At that point, we'll install our gas analyzer. We're going to start up the vehicle, and as the vehicle starts to run, HC and CO will rise to their maximum levels. We're going to record those readings. Then we're going to let it warm up 3 to 5 minutes. The levels will then drop if the catalytic converter is doing its job. Then we're going to record the lowest level readings. At that point, we'll compare these two readings together, and we should have a 70 to 90% drop in the readings. Let's start up the vehicle. We can now see our HC and CO are climbing. Catalytic converter is in the process of lighting off. Now they're beginning to drop. As the catalytic converter warms up, these levels should drop. The CO level is now dropped down to below 0.05, and the HC is now down below 100. The longer the vehicle runs, the catalytic converter will continue to light off. At about 500 degrees, it's 50% efficient. Now that we have our readings, we take the highest reading and the lowest reading, and we make a comparison of those two. What we're looking for is a 70 to 90% reduction in the gases, especially the HC and CO coming out the tailpipe. Now this can be done with NOx, however, the vehicle needs to be driven under a loaded condition in order for this to happen, or you can possibly use a dynamometer. We're going to perform a light-off test. The reason for this test is to see if the catalytic converter has the ability to light off in a specific amount of time. We need to start with a vehicle that's cold, or the catalytic converter being cold. The vehicle has to have sat for 30 minutes or longer. We're going to start the vehicle up, and we're going to watch our HC and CO gases. What we're looking for is the highest level that the gases go to on the initial startup of the vehicle. Then we're going to let the vehicle warm up for 3 to 5 minutes, and we're going to see what the lowest level of these gases are. Then we're going to make a comparison to see if we've lowered the emissions levels on those gases somewhere between 70 and 90% to have a good, efficient catalytic converter. This can also be done with NOx. However, NOx conversion needs to be done with the vehicle either on a dynamometer or driving on the roads. We'll start the vehicle up. We can now see our emission levels climbing. We have HC and CO that are around 600 or 700. Now we can see the levels dropping on the CO. CO levels are around 1.0, and the HC is around 260. Our levels are now down very low on the CO. CO is now down to underneath 0.220%, and the HC is down pretty near 75%. And we can see these levels are still dropping. This catalytic converter looks fairly good as compared to when it first started up in the levels that we had. These look to be about our final readings. We have 0.11 for CO, and we have probably about 30% for HC. These levels are very low as compared to when we first started it up when the converter wasn't lit off. We can see by these readings that the efficiency of this catalytic converter looks to be very good. When we took the highest readings that we had and then looked at the lowest readings that we have now after the vehicle's warmed up, this catalytic converter looks in fairly good shape. We recently brought in a 2005 Toyota 4Runner. The consumer's complaint with the vehicle was decreased fuel mileage. We took the vehicle in and didn't apparently have any signs of any problems with the vehicle. It seemed to run fine and no check engine light on. So we did a 5-gas analysis on the vehicle, and these are the numbers that we came up with. The hydrocarbons was 0.1. The CO levels were 2.48. Our oxygen levels were 0.12%. The CO2 was 13.9, and the lambda was 0.937. We did an analysis with our Ansed calculator, and this is what we came up with. It appears that the CO levels had failed. Also, the lambda calculator appears to tell us that the system's running rich. The most likely cause with the problem with this vehicle is a plugged air filter. So the first thing we did was check the air filter in this vehicle, and by obvious signs we see that the air filter is definitely plugged in this vehicle. We replaced the air filter and retested it. This shows you that the Ansed calculator is great for diagnosing the vehicle with gas analysis and lambda calculations. We recently brought in a 2000 Cavalier. The customer's complaint with the vehicle was the check engine light was on, and they had a noise underneath the hood when the vehicle was cold that went away when it was warm. So we did a gas analysis on the vehicle, and this is what we came up with. Our hydrocarbons were 679. Our CO levels were 0.13. Our oxygen levels were 2.7. Our CO2 levels were 9.7. Our lambda calculation was 1.13. The Ansed calculator came up with an analysis on this. The results were hydrocarbons has failed on this vehicle, along with the oxygen and the CO2 levels. The most likely cause was a diluted gas analyzer sample. However, we checked that and everything seemed to be good with the leak check on the analyzer. Option 2 was exhaust system damage. So we did take a look at the vehicle. We did a smoke test on the exhaust system and found that the exhaust manifold was leaking. After replacing the manifold, we cleared the codes in the vehicle, drove it through a dry cycle, and the codes didn't return. We gave the vehicle back to the customer. You can see that putting these numbers into the Ansed calculator led us down a path to diagnose this vehicle much easier.